Hi there, this is Shubham Mittal from deciphertechnique.com. Today we are going to study about the analog to digital conversion. The analog to digital conversion is very important step in digital signal processing applications because it converts the real world analog input into the digital signal. Let's see a small block diagram of how the digital signal processing occurs in the real world. We have some source of information or message or any signal in analog form. We have analog signal. We convert it into a digital signal using A to D converter, which we are going to study right now. And then this digital signal is processed by a digital signal processor, and then this DSP, digital signal processor, outputs a digital signal itself, and this digital signal is again converted back into analog signal using digital to analog converter, and that gives an analog output. This is the typical diagram of usage of a DSP in the real world. This is the block diagram of analog to digital converter, analog to digital converter. Shortly we can write it as ADC. Okay. So this analog to digital converter consists of sampler and quantizer. These are the two main components of the analog to digital converter. It accepts analog input signal. The sampler converts the analog input signal XAT into a discrete time signal XN. What do we mean by analog signal? Analog signal is a signal we have already discussed in the previous video, having the continuum of the amplitude as well as the continuum of time. It is continuous in time as well as amplitude. So this is an analog signal. We sample the analog signal to convert it into a discrete time signal. Discrete time signal means the signal exists only at discrete intervals of time. So this instants of time are denoted by n and the signal is denoted by xn. Then this discrete time signal is fed into a quantizer. What quantizer does is it maps the continuous amplitude into a discrete set of amplitudes. Let's say the amplitude ranges from 0 to 5 volt. We can divide the 0 to 5 volt into some 4 intervals. Let's say one interval is of 1.25 volt. So 0 volt, 1.25 volt, 2.5 volt, 3.75 volt and 5 volt. So we have divided this 5 volt interval into 4 parts. So quantizer, what quantizer does is it converts the dynamic range. It converts the dynamic range of this analog input signal into a fixed set of levels. So quantized discrete time signal is obtained XQN. This is the digital output. Why it is called digital? Because it is discrete in time as well as discrete in amplitude. Quantization results into the discretization in amplitude. We are discretizing the analog input signal in time as well as amplitude. Let's see this signal. This is the amplitude axis and this is the time axis. This is the analog signal represented by this black color. This is the analog signal. Whenever we feed this analog signal into the sampler, we get these samples denoted by this red circles. These are analog. These are sampled versions of analog signals. So these samples are obtained at the respective heights. These are the analog signal sampled at instants. Let's say I name these instants as n is equal to 0, 1, 2, 3, 4, 5, 6, 7. So we have 8 samples from 0 to 7. So we have 8 samples here. What we are doing is we have uh, fed the analog signal into a sampler and we got discrete time signal. This is the discrete time signal in red. Now if the discrete time signal is fed again into a quantizer, what quantizer is doing here is that it has divided the dynamic range. This is the dynamic range. Let's say it was somewhere around 8 volt. Okay, let's say this was 8 volt. This is the maximum 8 volt amplitude. So what this quantizer has done is it has divided the dynamic range into 8 intervals. 0, 1, 2, 3, 4, 5, 6, 7. So it has divided it into levels. We have 8 levels starting from 0 to 7. So quantization levels are represented by this purple dotted lines. So whenever you feed these samples into quantizer, the quantizer maps the signal amplitude to the nearest quantization level. Let's say this second sample at instant n is equal to 1. This second sample is having amplitude of something 4.5 above. So it has been mapped to 5. And this is slightly this third sample at n is equal to 2 is having the amplitude slightly less than 5, but still it is mapped to quantization level 5. Similarly, this 8 volt sample, this at n is equal to 3, is mapped into quantization level of 7. Likewise, all the samples have been quantized. After having quantized the sampled version, we get the digital signal. This is the digital signal. In the blue, we are having digital signal. This is the digital signal. So we can readily see that there is some quantization error. Although the signal level was slightly higher than 8 volt, but we have quantized it to the 8 volt and correspondingly we have written the 7 level. We have assigned the level of 7 to the sample. So we have missed some information here. So this is the quantization error. We will look into it at a later part of this video. These quantization levels can be written like this. So the samples can now be written as this. Simple numbers. First sample is represented by 2, second sample is 5, third sample is 5, fourth sample is 7. Likewise, we are having digital signal. This is the digital signal actually. These are the digits. So this is the digital signal. Now, this digital signal can be coded into a bit stream using binary encoder. If we use very simple kind of binary encoder, 3-bit binary encoder, why we have used 3-bit binary encoder is the fact the maximum value of this amplitude is 7. So we can represent 0 to 7 using 3 bits. Here we are using 3 bits to represent a level. So 010 is representing 2, then we are using 101 to represent 5. So these are the very conventional way of representing the levels. Okay, let's discuss the first block in the analog to digital converter, that is the sampler. It does the sampling process. What is the sampling process? I can denote it using this block diagram. So this sampler just samples out this value. This is written as like this. It samples out the values at every instant t. So we are having sampling frequency fs is equal to 1 by t. The analog signal, it takes xat and it converts it into a discrete time signal. Xn is equal to xant. So whatever the signal we are having, we are taking the values only at instants, at every instant spaced at t. Let's say I am having this signal. So what I am doing is I am taking the signal value as 0, t, 2t, 3t and so on. So we are varying the value of n. N is ranging from 0 to, let's say, infinity. And likewise I can take the values on the negative side also, because it is time. I can take values at minus t, minus 2t. This is the mathematical expression I am trying to say. Xn is equal to xa nt for n is equal to minus infinity to infinity. From our previous discussion, we already know analog, cosine, or rather say sinusoid. signal. Sinusoidal signal. This is the sinusoidal signal. Xat is equal to a cos 2 pi ft, where f is the analog frequency and theta is the phase, t is the time. So when we sample this analog signal, we get this sample signal is equal to xa nt is equal to a cos 2 pi f nt. We have simply replaced the value of t by nt is equal to a cos 2 pi fn 1 upon fs. We can write t is equal to 1 upon fs. So we have written it here like this. Then a cos 2 pi fs f by fs n plus theta, and this f by fs can be written like this f. This is the digital frequency. This is the normalized digital frequency. Why we are calling it normalized? Because this digital frequency will range between minus half to plus half. So this digital frequency is having the units of cycles per sample. How we can see it? F is having the unit cycles per second and fs is having samples per second. So when we write it like this, so we get cycles per samples. So this is the unit of normalized digital frequency. From previous discussion, we already know digital frequency ranges from minus pi to pi, and this frequency f ranges from minus half to half. Also, omega is equal to 2 pi f is equal to 2 pi f by fs using 3. Using above relation, we have written it like this, 2 pi f by fs, which implies that 2 pi f by fs ranges between minus pi to pi. Solving, we get the range of analog frequency. The analog frequency, the continuous time frequency f, is ranging between minus fs by 2 to fs by 2. So here only we can see that the maximum value f max is equal to fs by 2. So the maximum value that can be processed by a sampler is f max is equal to fs by 2. That is the sampling frequency that decides how much frequency it can handle, the sampler can handle. Multiplying the above equation by 2 pi, we get this relation. What this relation says is the angular continuous time frequency is limited between minus pi by t to pi by t, where t is the sampling interval. T is the sampling interval. Or minus pi fs to pi fs. So conclusion of this mathematics is this: f max, that is the maximum continuous time frequency of the analog signal that can be processed by a sampler, is fs by 2 or 1 by 2t. And the maximum angular continuous time frequency or angular frequency of the sinusoid or angular frequency of an analog signal that can be processed by a sampler is pi fs or pi by t. So these are the highest frequencies of analog signal sampled at sampling frequency fs. So here it is important to state the sampling theorem. Sampling theorem states that if the highest frequency contained in an analog signal xat is f max is equal to b, that is, we are saying that the signal is band limited to b hertz, and the signal is sampled at a rate of fs greater than equal to 2 f max or twice the bandwidth, 2b. Then xat can be exactly recovered from its sampled values using the interpolation function gt is equal to sine 2 pi bt upon 2 pi bt. So this is the sinc function. This is the sinc function, sinc bt. Using the definition, sinc x is equal to, I can write it sine sinc 2 bt. Pardon. Sinc 2 bt. Using the definition that sinc x is equal to sine pi x upon pi x. Thus, XAT may be expressed as, using this interpolation formula, we can express the analog signal as XAT is equal to the infinite summation of these sinc functions. The infinite summation of sinc functions results into a new analog signal. XAT is equal to infinite summation over all the samples. So this is the sample. This is the discrete time signal we are having, and this is the sinc function. So we are delaying the sinc function and multiplying it with the sample values to get the analog output.